finally, to differential and integral calculus. Differential calculus today, yay, derivative. Finally, some calculus besides just limits. So check this out. I want to remind you of the big ideas of the definition of the derivative. Make sure you can do the tedious ones, and definitely make sure you can do the quick ones, because they're the ones you'd see on an AP test. And then get you a little bit of a challenge in there. See if you can not just recall, but also think. And that'll be it. So here we go. The first definition of the derivative, or often just called the definition of the derivative, is the idea of finding slope, trying to find instantaneous or tangent slope at a point. Now you could say, hey, on this curve, I want to know what is the slope at that point A. And you can't find slope at a point, because how many slopes are there through a single point? If I draw lines through this point, how many different lines can I draw? Infinitely many, okay? I can, however, take slope through 2 points. So I need another point. Let's call H a little gap, a little delta x, and many books call it delta x, not h. If I start at h and go start at a and go h over, that puts me at a plus h. Now, in terms of the two y values, at a, I'm looking at f of a and f at a plus h. I want the change between those two. What do we call slope between 2 points? Or a line through 2 points. That's a secant line. A line between 2 points is a secant line. But we want to approach the line or the slope at a point, which we call the tangent line. All right. We're going to use the first definition to find the slope, tangent slope, at A, which we call the derivative. All right, now, the points we're going to use are this first point, A, F at A, and that second point, A plus H, F at A plus H. Oui. What's the slope between those 2 points? F of A plus H minus F at A. That's the change in y, or the rise, over A plus H minus A, which simplifies to H. That's the run. H is the run. That makes sense. It's how far we're going over. That's obvious. Now, every definition of the derivative has different notations and different looks, but they all boil down to the same two ideas. Slope between 2 points, approaching slope at L point. We have the slope between 2 points. How do we approach the slope just at A? So we can try and get this point closer, oops, I missed, and this closer and closer and closer. How do we make that process happen? A limit. Yeah, we take H, we say what happens as those points get closer together. Well, that means the gap shrinks. The gap is H, so H goes to 0. Notation-wise, we call that the derivative. This, in Newton's notation, is called f prime at x, h, a. What did I just find the slope at? A. It's f prime at A. It's actually not Newton's notation, by the way. He had a little dot above his, and he called it a fluxion, not a derivative. He called it fluxion. So, if you want to really sound historically not smart, say, well, let's find the fluxion of this function. And nobody will know what you're talking about. Now, let's go on to the second part. The first definition. Now, say I gave you that question, and I said, hey, use this process to find the slope at 2. And you could do that. And then I said, all right, now use that same whole process to find the slope at 3. And then you'd have to do all this work again. And then I said, now use that same process to find the slope at 5. Now, at some point, wouldn't it be tedious constantly doing all those different calculations with different a's. It would get boring, right? It would be logical then to say, well, forget this nonsense. I'm going to just give you a rule that gives me the derivative at any x, not just a, but in any x. If I do that, then rather than a, I'm going to say, let x be any point on the curve you want. I'm still going to create a gap to get a second point at x plus h. The y values will be f of x and f of x plus h. And I still want to focus on slope between those 2 points, approaching slope at just x. Now, this is not going to just find the slope at specific a, but the slope at any x on the curve. Let's bypass this part and just go straight to the definition then. That derivative would be the limit as, actually, I'll come back to that. What's the slope first? What's the slope between those 2 points? F at x plus h minus f at x over h. X plus h minus x is just h. Now, to get those two closer and closer together, remember h is the how far I'm going over. To get those two closer and closer together, I need to take that gap down to 0, which means I need to take the limit as h goes to 0. What did I find? F prime at s, right? Now, the answer to a problem like this, will it be an actual number or a function rule? This one. That's a number. When I say, hey, find the slope at constant 2, there's only one slope at 2, so 7, whatever it might be, all right? But is this a number or a rule for slope at any point? It's a rule. So this is a function of x. It's going to be a function. This will be a constant, a number. All right. The same idea applies when you look at this a little differently, just kind of different approaches in different situations. Say you also, going back to wanting the derivative at a specific point A. You could get the same result of the numerical slope there by approaching it a little differently. Rather than a gap, you're just going to create some other point x away. X could represent any point on the curve. A is set in stone as a constant. Now this is going back to trying to find the slope at an A. So it should be a numerical value, an actual numerical slope at that one specific point. The points and the slope, let's just bypass that. So what's the slope between those 2 points? F of x minus f at a per change in y. What's the change in x? X minus a. So you can see the slope's a little different. The denominator, or the slope's different. The denominator looks different. The limit's also different. There is no gap to take to 0. Per se, we don't have the gap named, but we can get the points closer together by taking one point closer to the other. What do I take? A towards x or x towards a? X towards a. So I say the limit as x approaches a. X can move, a can't move. Okay, so a can't approach x. It is what it is. All right. Last idea here. Sometimes, for reasons that we'll talk about, you want to look at the limit at a certain point, not by using the point itself, but by using a point on either side and gradually getting both of those points closer and closer together, equal distance on either side. That's why they call it the symmetric definition. We still approach the slope at x. So it's the slope at a point between. And you could do this with a numerical point. So it could be at some a, but Typically, you'll see it at a varying x. What is the slope, or what's the slope? Let's go down straight to the definition in order of time. What's the change in y between those 2 points? Oh, wait, let's actually name them. So this is a gap problem again. So I'm going to let h be the symmetric gap on either side. So if I go x plus h to get the larger point, it would be x plus h. If I start at x and subtract h, that would make the lower point x minus h, right? All right, now the slope. What's the change in y? F of x plus h minus, okay, over the change in x. X plus h minus x minus h. X plus h minus x minus h is 2h. You actually get 2 h's there. That's because you have a double h gap, yeah? How do we get the points closer and closer together? What does the limit have to do? Take the gap to 0. Gap to 0. This, I forgot to do notation here. This alternate, what is the derivative at? Derivative at a. What is this the derivative at? A or x? X, okay. All right, different approaches for different problems. This is more of a starting calculus 1 problem. So I'm going to try and save you some time, all right? If I asked you to use the definition of the derivative to find that derivative, could you do it? I'm saying doing all the algebra and rationalizing the numerator and all that stuff, you could do that? Okay, if you say yes, then cool, let's just let it go. If you say no, then you can try it on your own and I'll look it over. But I don't want to waste your time making you do these tedious long-way derivatives if you know you could do them without error. So are we good? Same goes here. You need to be able to do those, and on a college exam, you would be probably asked to do that, but you'll never be asked to do that on an AP exam, all right? What you will be asked to do on an AP exam, and a little easier to grade, is to go the other way. Given the limit derivative, do you recognize what you're being given? You're going to get a mixture on the AP exam and in my exams of plain old normal limits and limits that are specifically definition of derivative questions, and you need to say, oh, I recognize that as a definition of the derivative question. So all these are definitions of the derivative. And for all of those, we'll do one together. I want you to do this. First of all, tell me which of the definitions of the derivative is that. First definition, alternate definition, symmetric definition. That's alternate because x is approaching 3, there's no gap problem. Alternate definition. In this problem, this is normally the alternate definition numerator. What's the function, obviously, for this problem? The function must be absolute value of x. And at what point is this derivative? Is it at a specific x, or is it at any x? Is this finding the derivative at a specific number, or just at any old x? At x equal 3, okay? All right, that's what I want you to do for all these. Try these. Feel free to talk them over with your math amigos, and we'll go over them in a minute. If you are not with me, let me know. we doing? All right, are we ready? Or just finishing? Okay, do you agree with my first three? Okay. D, what kind of definition we got there? Symmetric. What is the function? X cubed plus 3x, and at any x or at a specific x? Any x. It's a rule, not a number. All right, now, what about this one? Symmetric, alternate, first definition? It is the first definition at a point. So f of x is x cubed plus 3x, and this one is at x equals 4. Choose that. All right. Next. All right. What did you say? First definition. F of x is x cubed plus 3x. At a point or at any point? At x equals 4. It's the same as that one? Yeah, this is actually the same as 76. Now that actually makes it quite a bit more difficult to locate, and it feels like 76 is out of nowhere. In that case, you want to use this as your guide for what the function is. All right, last but not least, this is the hardest one, if there is a hard one. Which definition? X goes to, actually you can look at this two ways. I intended for it to be alternate because x is approaching a constant. Now you could actually say symmetric with x instead of 8, or not symmetric, as first definition with x instead of 8. That was not my intention. Alternate definition. F of x is? Oh boy, that's rough. So here, f of x minus f of a over x minus a. Now with that, what's f of x? F of x is 4 plus x cubed plus 3 times 4 plus x. And at x equal what? What value are we approaching? X approaches 0. Now, if you were to do that, let's see, would that work? So if you said, do you agree it looks just like this one, but with x instead of h, yeah? So could you say this exact same thing? And the answer is, yeah, you could actually. Would these have the same derivative? Feels like different function, but the point is different. What's this derivative, just for fun? 3x squared plus 3, and what is the derivative specifically at 4? 16 times 3 is 48 plus 3 is 51. What about this guy? A little bit of chain rule there. What's the derivative? Not too bad. What's the derivative of 4 plus x quantity to the third? 3 times 4 plus x to the second times the derivative of the inside, which is just 1, plus the derivative over here, which is 3 times the derivative of this, or 3. What about f prime then at 0? That's 3 times 4 squared plus 3. Is it the same? Okay, so that's just perspective, really. All right. Okay, look at the back side. Do you remember differentiability? It's the ability to take a derivative, to differentiate. Give me 3 reasons why you cannot take a derivative. Sharp turn. You'll see corner if it's linear. You'll see cusp if it's curved. What else? Another reason you might not be able to take a derivative. Okay? Here, look at this curve here. What is f prime at negative 8? I don't know. There's not even a point there. So think that more generally as continuity. You cannot take or discontinuity actually. You cannot take a derivative at a discontinuity, at an asymptote or a hole. The derivative doesn't exist there. Okay? Think about it in terms of the definition of the derivative. It's hard to say, shucks. It's hard to say, hey, the definition of the derivative at A, if f at A doesn't even exist. So it just all breaks apart. All right, last but not least, the one that is commonly forgotten or mangled. I started you off. V. Vertical, okay, so then excellent job. Vertical asymptote, which is not quite correct because that is the same as discontinuity. It's not vertical asymptote, it's vertical tangent, vertical slope, okay? There is a vertical tangent slope. Now that's logical why that's a problem, because if it's vertical, then what's in the denominator? 0. You have undefined slope. Give me a function that has a vertical slope at a point. Can you think of one? Question. What? X equals y. Oh, well done. That's not a function, but now you're on the right track. Let me go one better. That, you're right, that does have a vertical tangent. That's absolutely true. Good point. I'm just going to stick with that. Yeah. Okay. What about this? Does its derivative exist at all points in its domain? What's its domain? Greater than or equal to 0. What's the derivative? 1 over 2 root x. What point in its domain does the derivative not exist? 0. And that's because at that point there is a right? Differentiability implies continuity. If I tell you the derivative exists at a point, you can be sure that the curve is continuous at that point. It's not necessarily saying the same the other way around. In other words, the converse is not necessarily true. If it's continuous, must it be differentiable? No. Give me a counterexample. Sharp turn. Okay, that's continuous, but not differentiable. All right. This has two types of problems, one of which is a total layup on an exam. The other one's much more difficult. If I gave you a graph that said, like this, and I said, at what point is f of x continuous but not differentiable? You just say A. Okay, easy enough. That's the easy kind. The harder point is when you get one that's more of a free response or open response kind of question, and you're asked to prove it. All right, yeah, okay. You can't have a derivative at a sharp turn. Prove it. Why not? Let's use this as a guide. Prove that the absolute value function, the v function, is not differentiable at 0. Prove it. I know there's a sharp turn there. Prove why that doesn't work. Prove it. I suggest you start with use the alternate definition. You want to do this one together? All right, great. Let's just have a doodle here. And 0 is definitely going to be one of my points of interest. And the alternate definition doesn't use a gap of h. It uses some point x. Now that x could be on this side or on this side. There's no reason it has to approach from the right. Now, in the alternate definition, let's start by saying the derivative at 0 equals, and when you're asked to prove things with derivatives, you almost always work in the definition of the derivative, right? So if this is truly, if the derivative is 0, then it must be the case that the limit as x goes to 0, alternate definition, what's the slope? F of x, in this case, let's use absolute value of x minus absolute value of 0 over x minus 0. Do you agree that that is the definition of the derivative alternate stuff? All right. So, okay, I can do this as a cleanup here. This without the zeros becomes this. Okay, great. I don't see the problem. Why not? That's the definition of the derivative. So let's move on. What happens? Why does it break down? What? 0 over 0. All derivatives are 0 over 0. That's not the problem. Every derivative is 0 over 0. Okay? What is the limit if I use an x above? If I look at the slope here and say slope, get closer, slope, get closer, slope, get closer. At positive x's, like 0.1, what is that slope approach? 0.1 over 0.1 is 1, yeah? But what if this limit, if it's the limit, I should be able to approach from the right and the left. And if I approach from the left, the limit as x approaches 0 from the left is negative 1. If I look at this slope and this slope and this slope and this slope, those are all negative 1. Well, the fundamental truth about limits is if the one-sided limits don't agree, then the limit does not exist. The limit does not exist. And if the derivative is the limit, then the derivative does not exist. So that sharp turn is a no-go because the one-sided limits won't match. In order for differentiability to happen, it requires local linearity, okay? Which is to say, if you zoomed in, it needs to look linear across your screen. No matter how much you zoom in here, it will never look linear, ever. All right. That's good. Do you recall your derivative rules? Lightning round. Here we go. Eric, what is the derivative of a constant? 0. Paige, what is the if you have a constant times a function? I'll give you an example. If you have 2 times e to the x, what can you do with that 2? Pull it out. So this is the same as the constant times the derivative of the function itself, right? If you have a coefficient, that coefficient can be just dropped out first. The power rule, the greatest of all math shortcuts. What is the derivative of x to the n? Kendall.
N times x to the n minus 1.
Right. We bring the derivative, the exponent down and drop it by 1. Okay. The derivative of a sum. Nate? Yeah. The derivative of a sum is the sum of the derivatives. Is that true for products? Is the derivative of a product equal to the product of the derivative? No. Let's see. Jordan, what is the product rule? All right. I left out my arguments, but you get the point. All right. That's the product rule. Quotient rule. There's a song. Amanda, what is the quotient rule? Low. It's low. Low, which is G. D. Low D high. Okay, low D high minus high D low over the square of what's below. Now, and she says over low, yeah? Me, I was taught low D high over high minus high D low over the square of what's below. What else? Low D high minus high F D low G prime over the square of what's below is G squared. Okay? All right, moving on here. Claire, what's the chain rule? If I have a function within a function, then how do I take the derivative of a function within a function? What? F prime, the derivative of the outside with the inside, same. So F prime of G times G prime times the derivative of the inside. Derivative of the outside with the inside the same, times the derivative of the inside. Derivative of log, Isabel? 1 over x. Derivative of e, Julia? E to the x. That was an easy one. Cassie, derivative of sine? Cosine. Hunter, derivative of cosine? Negative sine. Now we're starting to get in some that might be a little rusty. Ian, derivative of tangent? Secant squared. Anybody, derivative of cotangent? Oh, you guys are good. Derivative of cosecant? Negative cosecant, cotangent, and derivative of secant, secant tangent. Okay, get those back in your brain. I know you knew them last year. Get them back in. Now, here's the challenge to you, all right? Every one of those rules, every one came from the definition of the derivative and proving them to be true. I'm not going to make you prove all of them. Back in the day, my first year, I said, you cannot use any shortcut until you prove it. And wow, that year was rough, I'll tell you what. I'm going to just ask that you get a little practice. Would you, your goal, your job, should you choose to accept it, and you do, because I don't have a choice, is to prove the derivative of sine is cosine by using the definition of the prove it. I suggest you use the first definition. Please work together and bounce ideas off each other. I did have some people, about half the class, they didn't get it. Class, because they kept trying, they didn't just throw their hands and quit. So wrestle with it, even if it hurts you in your butt, it's better than not fighting it out. I gave you lots of hints there. You would be wise to use them. I know that doesn't narrow it down a lot. You know a lot of identity, so make sure you choose what I want. Talk it up. What identity do you have? Come on, don't look down like you don't see you. I'm right here. What identities do you have? Double angle. Good idea. There's no double angle here, but you're on the right track. That's a sum, I think. Yeah? So do you remember sine of A plus B? That's close. Three famous limits that any calculus student worth their salt should know. Well, you guys need to work on your collaboration skills. Look, you didn't get it. You're doing portion. You guys are checking. That's good. Oh, you're almost there. You're so close. You're done. Run it in. Run it in. You're good. So, say this was a 4. Could you put a 4 out front? Because it's not the way to keep the limit, right? Absolutely. Okay, so we're getting there, or some people are there, and I'm very impressed. If you rearrange a little to group the signs, the reason being I'll show you in a minute, but if you put those together, there's a sine of x and a cosine of h, take away 1 over h, yeah? Now, looking at that, as I said to Kendall over there, if that were a 4, what could you do with that limit? That 4, you could pull it out front, because it's not really related to h's behavior. Same goes with sine of x. Sine of x is a function of x. It has nothing to do with the h. It's going to matter what h does, and so if I pull that out front, I get something like sine of x times that famous limit equals, you should know it, 0. It's 0. Okay? Sine of x times 0. Now, the green is the single lone term that had nobody to join with. It's this. What shall I do there? Take out cosine. It's an x function, not an h function. And what does that limit approach? 1, and therefore the derivative must be cosine. Okay, last but not least, do you remember your implicit differentiation? Should we crank this out real quick just to remind you, or no, you're good? It's over in a little bit, or no? Crank it out? Okay, go for it real quick. See what you think. I'll follow along after you in a couple seconds later, and we'll verify we remember this well. This is implicit differentiation, which uses Leibniz notation. Or Leibniz got mocked mercilessly for his idea. Okay, that's how I'm getting 3y minus 4x over negative 3x plus 2y. What if you have 4x minus 3y are opposite signs in top? Are you out already, or could you be right? You could still be right as long as every sign changes in the top and the bottom. So if you had the opposite signs, that would mean you moved your dyx's to a different side than I did, which is fine. In which case, if you had this, then you would have 3x minus 2. Both of those, or either of those is fine. All right, cool. Homework questions. Let me give you answers to the old replacement problems. This is homework 5? Yes, review 5? Alrighty. I'm on the, 8 was D&E, that was a replacement in the front. Going to the back. Positive and increasing. I said you could use your calculator if you were a real stud and you could do it without a calculator. How do you find where a function is positive? By finding where a function is positive, where its graph is above the axis. So you can find where it's positive by finding where y is positive. How do you find where something's increasing? By finding where its slope or derivative is positive. So I could find where its function is positive, find where its derivative is positive, and then take the intersection between those two sets. This is a no calculator answer because I just felt like doing some calculus instead of using my calculator. If you had decimal forms, that's fine. Okay. Number 16, I had some disagreement on this, so I don't know if I did it wrong or they did it wrong, but there were a lot of different approaches to this. The problem that I have is that if I'm not very good with the Inspire. In the Inspire, if you put it in conic section form, then the functions like the intersection points are wonky. You have to use some kind of box or something. You know what I'm talking about? I didn't either. That's what somebody else said. The calculator can do conic sections, but I can't remember what the gimmick is. I actually solved this for y by completing the square. This is my complete the square equations. Then I put the line in and found intersection points. Some people also substituted this into the conic and played with that, and that's fine too. But let me know if your answers are different. Are your answers different, or did anybody get those? You did? Oh, super! Yay! At least Jordan and I are in agreement. All right. If you disagree, then we'll talk about it. 18. Did you get E? Okay. Moving on to 19. 19. Oops. Okay. How many times, if any, must it pass through x equals 2? Okay, there's two answers. Twice or at least twice, which is at least twice. Okay, now this goes to reading too much into the table. In going from 7 to -3, if it's continuous, must it pass through 2? Yes. Must it pass through once? I mean, it could be going crazy through 2. It could be going through 1,000,000 times. We don't know. And so it's at least twice. At least twice. With a lot of writing, right? This I replaced. Never mind. Sorry, real quick. These were, what'd you get for this? Did you say yes as an IVT kind of thing? Okay, so we're cool. And these are your answers to that. One-sided limits there. Okay? If you have questions, work through them. I'll try. Oh, you were here for some period. Whatever. Just make sure I get it by the end of the day. Okay? Have a nice day. I'll see you in a couple minutes, 10 minutes.